To begin. Welcome to using data as evidence for argument in the AP research course. And so today, we're really going to focus on some best practices with data in AP research and how you can mentor students in producing better projects. And then also take some time showing you how Data Classroom can help you directly with some of those tasks. Um, I'm curious in the chat, how many of you are in attending a data classroom webinar for the first time today? How many of you are just joining us for this topic for the first time? Um, there's definitely a few first timers, so welcome. And this AP research is an area that I have to say I've only been hearing from people really strongly for about the last year. It was almost like this course kind of popped out of nowhere on our radar, but we started hearing from people who were wanting more help with mentoring their students with data activities, wanting more help with graph making and statistics for their students. And so I think that is something that we can help with. You might have also heard me chatting with one of our attendees in there when we were waiting to get started. And we were talking. I said, "Oh, Brian, are you teaching AP research?" And he said that he's not teaching that course directly, but that there is a lot similar with the research course that he's teaching and the needs of AP research. And I see that a lot. And in fact, I was at the International Science and Engineering Fair that was held in Columbus, Ohio last week, and I was very tempted to give my exact same talk from that event here, and that was 3 tips for better science fair projects, because I think that the world of competitive science fair and the demands of AP research actually have a lot in common. So I did slightly rework my talk, but I've borrowed from a few themes that I commonly will go to when coaching a science fair audience. But we're first going to talk about the specific AP research performance task guidelines and what I found when I dove into that. And then we're going to kind of go into 3 suggestions. One focusing on a topic with clear and narrow parameters, and that language comes directly from the AP research rubric for the academic paper. We're going to talk about beginning with the end in mind, which is actually a tip that I give to young scientists really at any level, or young researchers at any level, is begin with the end in mind. And you want to do a couple of thought exercises before you begin a research project. And also, finally, using stats to add confidence to the main argument. And I think that I saw statistics a number of times in the sample papers that College Board puts out for AP research. But I think there's with young researchers especially, you want to coach them to use statistics to add confidence to their main argument, not to find their main argument. And I'll kind of try to explain the difference to that, or the difference between those 2 things when I get there. If anyone has a question at any time, feel free to drop it in the chat. I've got 2 monitors up, and I've got one of them displaying the chat. So if you have a question, please pop it in there, and I'll do my best to get back to it in a timely manner. So let's go where we're headed. So let's step into number 1, the AP research performance task guidelines. This is the document that's up on the College Board website, which if you all have been teaching AP research, I'm sure that you are familiar with this. I have to say, when I looked into this earlier this year, when we started hearing from more AP research teachers, I was pretty surprised at how vague this document is. And I don't know if any of you had a similar experience, because I think that the academic paper is a really big task with a lot of very specific challenges. And I was kind of taken aback to see the scoring rubric and to see just, that really all that's listed for each of the scores 1 through 5 is just these 6 bullet points of what they're looking for. There's no sort of mention of data at all. And in fact, this caused me to dig a little deeper because I thought, oh wow, they don't even require data in the paper. Well, why are we getting so many inquiries from the AP research community? But then when I looked a little deeper, I noticed that in 2024, College Board put out 10 sample papers, and they listed what the score on each of those sample papers was. And 7 out of those 10 example papers contain data figures. Many of them contain statistics that went along with those figures. It's also worth noting that only 7 of the 10 of them uh, contain some visual presentation of data, but all uh, all 6 of the examples that were a score of 3 or greater all contained data. So that to me says that the College Board and their grading system, they're pretty serious about having data in the paper. It seems like while it's not strictly necessary, some presentation of student data in the paper is a pretty clear path toward a higher score in AP research. And I saw a whole wide variety of visual representations of data. I saw regression lines. I saw mean and error bar kind of graphs. I saw pie charts. I saw frequency charts. I saw stacked bar charts. So, a wide variety of what I kind of call the core statistical data representations, and really all things that are within the data classroom wheelhouse. So I think after looking into that, it made a lot more sense why so many of you in the AP research community had reached out to us. And so hopefully we can give you some just suggestions on coaching students in their use of data to fulfill these bullet points more toward the 5 end of the scale. And one going into point number 2 for today, one of those 6 bullet points in there is coaching students to focus on a research topic with clear and narrow parameters. And this goes directly with something that I've been telling the science fair crowd for years, is that smaller questions often make better research. It can be a little surprising to someone who's not from a research background, or maybe not familiar with science as a practice. But science it's often very surprising how narrow of a question science is addressing at any one moment. And the the thing about strong science and strong research is that it's wanting to make a claim and use strong evidence or have a high degree of confidence in that claim. And to do that, it works best when you have a narrow question and you've got a very well-designed experiment, or you've got a very good source of data, and you have a lot of replication on that. So at the end of your research project, you have a strong answer of saying, either this hypothesis is supported or it's not supported. But that is often a very narrow question. So I want to just kind of go through an example of a research project that I did with my students when I was teaching in Chicago public schools. And as an example of the question as it started too big was, how do females decide where to lay an egg? And so this was a research question that we had. But there's a lot of reasons why this is a big question. One, it doesn't even specify a species. So there's quite a bit of variation in the animal kingdom. There are quite a lot of species that have egg-laying females. this might not be a question we can answer in a general manner. It needs to be asked more specifically. Uh, there's in this also, how do they decide? It might be a very, very complex decision. So if we can narrow that down to more factors, that would be better. So as I worked with my students to narrow that question down, we narrowed it down a little bit, and it's still too big in this form. But how do female brown anola lizards decide where to lay an egg? So we've narrowed it down to one specific species, which is good, but we still have the matter of the decision, or how do they decide, is kind of too big of a question to answer with a single experiment. And so what we focused on is students who eventually kind of came to the idea that, okay, well, what are some things they might decide on? We talked about locations close to plants or far away from plants. We talked about wet and dry soil, and we had learned how reptile eggs are transfer water between the interior of the egg and the environment. And so we came up with this question of turned it into kind of a preference. And do female brown lizards prefer a uh, wet soil when deciding where to make a nest? And so now at this point, we have a very specific, focused question. It might not be as exciting as the first question of, how do females decide where to lay an egg? This kind of mystery of life question, but we've narrowed it down to something that can be answered with data. We've narrowed it down to something that can be a specific experiment, and I think that is exactly the task for your AP research students. Is they're going to have to um, create a narrow question that they can use data um, to answer. And again, if you all have any questions, um, feel free to jump in. I want to talk a little bit about how we put that narrow question, how that can kind of become an experiment, or can become many experiments. In its simplest case, we could see it diagrammed out like this, where we have this variable of soil moisture, and we could present the female with a dry or a wet choice, and then we could repeat that experiment times some minimum number of replicates. And this is always where I think you want your students to start asking themselves, can I get enough replicates for the experiment that I have planned? And unfortunately, there is no magic number of replicates that you should have in an experiment. It is dependent on a lot of factors. It is depending on, how much your answer varies. But what the kind of variation is. If 9 out of 10 lizards prefer wet to dry, you probably don't need very much data to make your case, right? But if 54% of lizards prefer wet to dry, then you're gonna need a lot of data to show that there is a difference between that there is a preference at all, because it's only a slight preference. So it's going to largely depend on, what that effect is you're trying to detect. As a rule of thumb, when I'm coaching high school students, especially in making a research project, whether it's for AP research or it's for some research competition, I would say that you should not add treatment groups to an experiment unless you can reasonably get 20 samples per treatment group. So if there's some reason, whether it's time or money or effort or space, that will keep you from getting 20 replicates per treatment group, then I think you want to make your experiment as narrow as possible. And so like a binary choice like this example would probably be appropriate. To show how you could make this into a bigger design, right? Same question of, do female brown and anola lizards prefer wet soil when deciding where to make a nest? But we could scale this up, and we could present our female lizards with 5 different choices of moisture. You can see it ranging there from 0 to 75. And this was an experiment I did with my students in our classroom in Chicago back in 2010. So it's been a while, but you can see here you could present a female with five different choices. However, remember, I wouldn't go to a design like this unless we could reliably get a sample of 20 per treatment group. So if you don't think you're going to have 100 lizards lay eggs, then you probably don't want to do a design this big. And in fact, some of them might, if some of the conditions are chosen very rarely, you might even need more than 100 to have good statistical power, to have good confidence in the conclusions you can draw from this. And so again, if a student comes to you with a design that looks like this is fundamentally sound, but you also have to consider the practical concerns of, how many replicates are you going to be able to get? If it's a survey, how many respondents are you going to get? If you have five levels of a choice, then I would say you would probably want to shoot to get a minimum of 100 respondents to that survey, if not more. And so that's just kind of a basic rule of don't add levels to a treatment, or categories to a categorical variable unless you're going to get at least 20 replicates per group. So that was my point number two and tip number one for today. Point number three and tip number two is begin with the end in mind. And this is a principle that I think can govern just about everything your students are doing in research. And when they set out to make a research project, you want to the extent that is possible, you want to try to think through every aspect of the project, all the way to the end. And by the end, I mean actually creating the product that you're going to use to communicate your research results. So you want to think about that research paper or that research poster you're going to use in your presentation, or the data figures that you're going to use in slides. You want to think about all of those things before you start a project and before you start collecting data. And if I could make one suggestion to that end, I would say to students, what will my graph look like at the end? And that is the one question I would use as an example, to your students, to say, okay, what is the graph going to look like at the end? And I'll give you a little bit of scaffolding to kind of show you what I mean by this. And so with our example question that we looked at before of, do female brown and knoll lizards prefer wet soil when deciding where um, to make a nest? What will my graph look like? You want students to actually sketch out, okay, what's a graph going to look like if this question is answered in the negative, there is no preference for wet soil, and what's it going to look like if the evidence supports the positive, there is a preference. And so this was an example of a student sketch that I had, and I've shared this in a webinar in another setting before. Um, but this is a student sketch of what the data would look like with no support for the hypothesis. And I like this sketch for a couple reasons. One is there is some subtle variation in the graph, right? The bars are not all exactly equal. There's a little bit of difference, sort of reflecting that there's some random difference there. But there is no clear strong preference in the number of eggs, which is on Y. They just wrote number, but number of eggs on Y. There is no strong preference there. And there there is you can see in there, there's some variance, but there's no strong preference. Also note that for this exercise, the numbers are not necessarily important. Um, at this point, you're just wanting to kind of show me what the trends will look like, right? And then conversely, this was the drawing of the sketch when the hypothesis was supported. So if there was a preference, what would that look like? And there's actually a couple of different ways the student could have drawn this. Um, there you've got this soil moisture where you can see it's progressively the bars are getting higher as you move over to the wetter soil moisture. So this kind of shows a clear preference for soil moisture. It could have looked different ways, right? It could have showed a preference for dry soil that also would sort of support the alternative hypothesis in some sense. I guess not if it's they prefer wet, but if they had a preference at all. It could also, show high bars for the 50 and the 75 and low for the rest. It could show high bars for, the 12 and a half and above and low for the 0. So there's a couple different flavors of how that would look. But in general, this is a showing of support for the hypothesis. But now when the student sets out to do this project, they're collecting these eggs. They are they're able to make sure they're collecting the right data. So they're saying, okay, well, I need to present these lizards with choices. I need to collect eggs, and I need to collect enough eggs so I can get bars that differ in height. This is sort of guiding, what they're doing. It's sanity checking the experiment that they have designed there. And we had a question in the chat. In the sample question, does it work as a yes, no? Because this amounts to create an experiment paper. And I would say this question could work as a yes or no, and maybe you can elaborate that on that. But I'm interpreting this question as sort of like, is this enough to write a research paper on? And I will say yes it is. And it's actually sometimes um, kind of surprising about how sort of uh, much you can write on the topic of a simple question. I think we need to look no further than the actual scientific literature for that, because the questions are often, quite small, but you can build a quite a strong research paper. And yes, in the sense of the question, in the way we have it phrased there, is it a yes no? And yeah, it is. And you will still answer that though with quantitative evidence, toward the conclusion of it's either in the end it's either going to support some preference or it's not. So you'll be able to talk a lot about, what confidence you have and convey your data with nuance there.
And Aaron, not only that, but during that whole process of like the hypothesis building and things, the students are going to need to justify why they think either yes or no. So it won't just be a simple yes, no answer. It'll be a yes or no because, and they can kind of show their thought process there. And especially with biology, nothing is ever yes, no.
Yeah.
So and there's always the variation in living things that are going to add to that the ability of the students to show off their thought process through the whole procedure.
Yep. And Brian's exactly right. It's that showing off of the thought process. It's that metacognition, which makes up the meat of the research paper. You can take a simple question like the one that we have, and then defending, what your prediction is, whether the answer to that question is a yes or a no. You have to dive into the scientific literature on egg laying species. You have to dive into physiology of the egg. So there's all this background and literature research that goes into a student in making a prediction, even for a relatively simple and straightforward question. Yeah. Um, so to kind of continue with that, with the beginning, with the end in mind. So I said, one, you want to have students think about what is my graph going to look like, and I think that is the one thing that probably is going to give you the most bang for your buck. It has the ability to really help students clarify what they need to collect in their data and how they need to do their experiment. But I also think analytically, these are two questions that I've got up there underneath the begin with the end in mind. These are really important for thinking about the analysis that you're going to do. What are my variables? So what are my variables that I'm going to record in this experiment? And what are my units of observation? In the case of the example that we looked at before, the unit of observation was the individual egg. And what are my variables? These are going to end up becoming the columns in your data set. If you're working in the standard tidy format that is pretty much universal in science, um, each variable is going to get its own column. And every unit of observation, so everything that you record is going to add a row to the data set. So you can think of these units of observations are rows and these variables are columns. So if we take a new example, does incubation treatment affect body mass at hatching? And I'm still working with baby lizards here in my example. What are the variables that I want to measure? And then what does each row of the data set represent? So we want students to think about that. And in this example, body mass as a numeric variable, body mass in grams, could be one of the variables. And then the other variable that we need is incubation treatment. What treatment were they in? Was it a high-low treatment? Was it a wet-dry treatment? Was it, a 0, 12% moisture, 25%, whatever those levels are. But we can reduce this down to answer this question. We need to collect data from on two different variables. We need to know body mass and we need incubation treatment. And we need to get this from multiple units of observation. So we need to hatch multiple lizards to get this. And so each row of our data set is going to represent a single lizard here. And I just kind of, put this up as an exercise. I don't really, we're not going to go through the solution here, but this is just kind of something to take away and we can talk through it. But again, you want to go through what will the data look like if the hypothesis is not supported? What will the data look like if the hypothesis is supported? With this, your response variable in this case is that body mass. And so body mass is going to be a numeric variable, probably represented on Y. And then your treatment is going to be some kind of categorical variable represented on X. And when we go look at examples, we can look at something similar to this. But you're going to have to, something that's comparing the averages in body mass between those two groups and some representation that's showing the variation around there is going to be needed. And if the hypothesis is not supported, we're going to see, no difference in average. If the hypothesis is supported, we're going to see those are different. And so you want students to be able to talk through that, think through that, ideally sketch that out for you on a whiteboard or a blackboard or a piece of paper, and think about, what they're going to do. I have to say, so often I don't see students thinking about their graphs until it's time to make their paper or make their poster. But I think that's far too late in the planning and the preparation process. Ideally, they would be doing that at a much, much earlier stage. Okay, and um, my final tip of the day, and I do have more of these, but these webinars, we like to keep them to these kind of bite-size things. And I also want to have some time to kind of play with some data on Data Classroom for a simple experiment. But use stats to add confidence to the main argument. And what I mean here is that you can take a simple graph like this, and your students should do this at the outset of when they have data. And you want to start looking at that data graphically and drawing a conclusion before you start applying stats. You don't want to wait until you have statistical results to start thinking about conclusions and thinking about in terms of support. You're going to start thinking about that right away from the first moment you get a look at a visual representation of your data, because stats should never be surprising. If the statistical result completely surprises you, even after you've taken a good long hard look at the data, then either you've made some mistake in the stats, or you're looking at the data in a completely inappropriate way, because stats are put confidence to a conclusion, but they shouldn't be a conclusion that runs contrary to what our eyes are telling us when we look at the data. So for example, this is a simple experiment where we had runners running both shod with shoes on and running barefoot, and we were looking at what their running cadence is. And so we can see that this kind of cluster of points for the barefoot runners is sort of shifted upward, and it looks like on average they maybe have a higher running cadence than runners wearing shoes, but there's a lot of overlap between the two groups. So it does look like there is a difference. It looks like the difference is somewhat slight, and there's a lot of overlap between the two groups. So I would say that, looking at this, when you see this, this looks like some evidence that those groups are different from one another, and you should be able to talk about the data in those terms, right? And so kind of thinking statistically in a stepwise manner, probably the next thing you can do in sort of the simplest sort of pre-statistical way to think about this data is you might summarize them with an average. And here I've displayed the average and the 95% confidence interval off to the left beside the points. And we can see that the average for the group that was shod was 154.1, and the average for the group that was barefoot was 167.8. And so again, putting some numbers to that, hey, in the first one I said it looks like on average the barefoot runners have a higher cadence. This is interesting, by the way, because there's a lot of evidence in sports medicine showing that higher running cadence leads to lower force on the joints. You're kind of taking more frequent steps, but they're sort of quicker and lighter steps, and they're not as jarring to the body. Um, and then, finally, when we go on to actually do some inferential statistics, this we've applied a t-test where we're looking for a difference in the average value between the two groups. And I've cut out the pop-up from DataClassroom. That's the kind of quick explainer of, why would you use a t-test in this situation, and how does it work? It's giving us this probability value of less than 0.01. And we would interpret this as, extremely strong confidence that there's a difference between these groups. Or another way of thinking about it, we could say there's less than a 1% chance of getting data with a difference like this due to random chance alone. So even considering all the variation and the overlap between the groups, this looks like a meaningful difference between the groups. And so I just want to point out that you want students thinking about statistics like this and applying it like this, where they're not just generating that p-value and spitting it out without ever having looked at the data and trying to say, oh, definitively, this tells me everything I need to know about the data. But they can when they visualize the data, they can see the nuance, they can see the overlap between the groups, they can form a conclusion, and the p-value becomes a kind of way of saying, mathematically, how likely is it to get data like these? And with that, I want to jump over and we'll play with this data set in Data Classroom for just a bit. And if anyone has a question, feel free to drop that in the chat. And I'm going to jump over. I'm going to jump over to the Data Classroom resource library. There are all sorts of data sets that you can use for practice that students can, with exercises they can work through in here. That is another tip I will say for AP research. Ideally, probably their research paper is not the first time that they're analyzing a data set. It can be very, very helpful to have them work through a number of data sets in the course of the course before they get to that kind of capstone event of making their own research paper. And I'm going to open up that data set. It's called Born to Run, analyze running cadence data. I think this one is typical of a lot of the kind of student collected data sets that I've seen for AP research. This could be, this is like I said, this could be a research question settled around do barefoot runners have a higher running cadence? Generally that's important for implications because there's research in sports medicine saying that, barefoot running might be easier on the joints in part due to due to that perceived increased running cadence. So if a student wanted to put an idea like this to the test, there's a wealth of research that they could use to sort of form a hypothesis to give background information. And these data were collected with kind of simple pedometers, so sort of pretty inexpensive equipment that they could use to test running cadence. These data were paired. So they had, I believe, 15 test subjects, and they tested each test subject both with shoes and barefoot. And so, kind of looking at the data, um, we'll start plotting this out. First, I'm gonna graph running cadence on here. And so we can look at the running cadence in steps per minute. We can see that the data range from down here about 13.7 steps, or sorry, 137 steps per minute up to about 182 steps per minute. And I could visualize these data a different way. We could look at the histogram, and we can see that the the mean value is somewhere here in like the 160 to 165, I'm guessing. Let me add the mean on top of there, and we can see what that is exactly. Looks like, yeah, the overall mean is 161. Um, but I'm going to go back to dot and line based graphs. So I'm over here at the control panel at the right. I really like to look at data this way until I have a very good handle on what's going on, because I can see every individual data point. So it just gives me a really good idea of what the data are. So right now I'm just looking at running cadence. I see the mean. The main question in this data set, or what the student was asking with an experiment like this, is, is there a difference in running cadence between barefoot running and running shod? And so we split these up, and again, it's already showing the mean and 95% confidence interval because I requested that um, before. And so, this is the kind of graph we could use. I'm going to go through and, we'll run the t-test. So if you're not familiar with Data Classroom, if anytime you use this graph-driven hypothesis test button, it takes a look at the data figure that your students have created, and it takes all the information that we can know about that. We can know basically you're comparing a number across two categories in this case. And so it will suggest a t-test if we're assuming normally distributed data. And it's, this table is explaining that logic. When we click calculate, it's giving us that pop-up here where it's saying, this is the test used to test for a difference in the average value of a numeric variable between two different groups. So this is again telling the student exactly at the point when they might be wondering, why am I doing this? This is explaining, why you're doing this at this point. And it lets them know that it's mathematically, it's weighing the signal, which is the difference in means, against the noise, which is the spread of the data around the means. And it's giving them a result there. And again, this is what we saw in our last example. However, I want to show you that if a student dives into these data in a more sophisticated way with their graph, it will lead them to a more sophisticated analysis. And I'll say, based on what I saw in the examples in AP research, they're not necessarily expecting your students to be experts in statistics. But they are expecting them to try and be logical. Okay, so there's a number of minor points I saw in the example examples there where there were things that were not perfect. And so, like, for example, I think that if a student wrote a very strong paper, made a good, clear argument, had a good method section with the data like these, they could probably score a 4 or 5, no problem. But I just want to point out that analytically, this student isn't accounting for their paired design with this graph because these runners, they use the same runners in both treatment groups, in both the shod and the barefoot group. They had each runner run twice. So what one thing you could do to account for that is you want to ask, well, are there just some runners that had higher running cadences than others and some that had lower? And how is that affecting the results here? And I'm going to add this test subject ID, and I'm going to add that by adding it as this third variable that I'm calling Z here. So I've got treatment on X, cadence on Y, and then test subject ID on Z. And you can see they're all color coded. This isn't very illuminating, but if you connect the dots like this, I just checked this box to connect dots with lines. Now this is actually pretty illuminating because this is showing the overall trend. And you see all those pairs are the same runner. And you can see the overwhelming majority of them have a lower running cadence when they're shod, and then the lines go up and to the right when they're barefoot running. There's a couple of exceptions. We can see that test subject M13 had a lower cadence when barefoot, and then same with F10 slightly lower, M8 slightly lower, and F13 slightly lower, but all of the others went up. Um, so 11 out of 15 had an increase. And if we go and we statistically analyze this now, it will guide us to a more sophisticated analysis. It will guide us to the paired t-test, which this is sort of the same. You want to know if there's a difference between two groups, but the samples are paired by an identifier, and it's taking into account how much of the variation is due to just differences between people. And so it's sort of factoring that out mathematically. So we again, in the end, it gives us a p-value. The general conclusion we draw isn't different, which again is why I think even if a student didn't do the paired t-test, they did the regular t-test there, I think they would probably still do all right in defending their research and their methods. But this is just to show you how Data Classroom can support students, or another tool as well could support students in the kind of analysis they're able to do. So we are just about out of time for the session today. We're at about 5 o'clock Eastern. If anyone has any questions, I'm happy to stick around for a bit. And let me put up my contact information before I turn off the recording as well. And just say if you have any questions at all about guiding students in AP research, statistics, experiment planning, happy to talk about that. If you have